So Luke, another week, another viewer's question.
Yep, to the teleprompter. So, we are asked, will the 3 subatomic particles in a proton eventually quantum tunnel out of the proton? Or can gluons pull them back however far they've moved? Well, you better explain what's inside a proton.
Well, okay, so let's start with protons, right? So we know that when we look into the nuclei of atoms, we find 2 kinds of particles, protons and neutrons. Okay, so the hydrogen atom has 1 proton, and then you get to helium, which is 2 protons, 2 neutrons. And if you make your way up the periodic table, you just build up your nuclei heavier and heavier with more protons, more neutrons. What was realized through the 1960s and 70s is that protons themselves aren't fundamental objects. Protons are made of things, and these things are known as quarks, not quark.
Not quarks.
Not quark.
Heard it here first.
Quarks. Okay, so let's draw a picture of a proton. We're going to use the board. Okay.
That was another viewer request.
Right. So
this is very exciting.
Proton.
Yep.
Okay. So what we've realized is that every proton and every neutron, they're made up of 3 quarks. And every proton has exactly the same quark content. It has 3 quarks in it. 1, 2, 3. Now, there are 6 different kinds of quarks in nature. The up and the down, charm and strange, top and bottom, or truth and beauty.
I've never heard them called that.
Yeah.
Well, yeah. Anyway,
So for our protons, they have an up quark, and a down quark. Okay? Now, these quarks are sitting there, but they're actually held together by the strong force. Okay, so it's the strong force inside the protons that keeps these quarks here. And so actually what we have is we have all these other little particles bouncing around. These are called the gluons, and these glue the quarks into the proton. And it's also the gluons that give us the strong force between the protons and the neutrons and hold the nucleus together.
Right.
Okay. So this actually is an exceedingly simplified picture of what a proton is. If there's anybody out there who actually does modeling of a proton, we know that there's a lot more going on. That quarks actually spontaneously decay into quark-antiquark pairs and going back together, etc. again. So, but this will do for the simple picture. So this is the internal structure, quarks held together by gluons. And the question is, will one of these quarks quantum mechanically tunnel out of the proton? Okay, or will the gluons hold it there? So now we need to work out what we mean by quantum tunneling.
Right.
So I'm going to hand over to you.
My goodness, what a...
Right.
Okay, so let's think about... I've got a hill here, without getting in the way too much. I've got a ball here, and I want to get it over the hill, over to here. Now, I've sort of given that away. I want to get the ball from here to here, and I have to go over the hill. Now, the reason why we physicists think about this system a lot is there's an awful lot of systems which are kind of analogous to a ball's rolling or sliding, really, around a hill. So this could be any sort of quantity down here. And what we want to ask is, okay, if I had the system which had this value of the quantity, what would happen next? So we'd usually roll down the hill unless it's going this way. In classical mechanics, there's a certain amount of energy represented by this height difference here. So, right, the gravitational potential energy. And if I want to get the ball from here to here, I have to supply that much energy. Otherwise, I don't get over the hill. What would happen is I would roll up to a certain point, say I gave it that much energy, I roll it up to a certain point, and then it rolls back down the other side. That's classically. In classical physics, we would call this a potential barrier. Yes. There is a certain amount of gravitational potential energy you need to overcome by giving this kinetic energy to get the ball from this side to that side. Right.
So what does quantum mechanics do?
Quantum mechanics, of course, makes things weird.
Yeah, okay.
Now, that's what quantum mechanics always does. There's a way of modeling. Let's take an example of quantum tunneling in the form of radioactive decay. So something like there's sometimes when you have a nucleus, you have a whole lot of protons and neutrons. You just said that stuck together, and every now and then it will spit out what's called an alpha particle, which is just a helium nucleus, 2 protons and 2 neutrons stuck together. And when we make a model of the sort of inside of the nucleus, we find that alpha particle, we can treat it a bit like this. There's a certain barrier that it would need to cross in order to get out.
So this barrier, if I remember my nuclear physics,
Yep.
this sort of uphill part, this is the strong nuclear force saying, I want to hold on to that alpha particle. Then that outside, that is the electromagnetic force saying that if the alpha particle was outside, it would, because the nucleus and the alpha particle are positively charged, they would repel. And so it wants to kick it off that way.
Yeah.
So there is a barrier that the alpha particle needs to overcome. But if I remember rightly, the alpha particle inside the nucleus doesn't have enough energy to overcome the top of this barrier.
That's right. So that's where things get weird.
So why is there alpha emission at all?
Well, so the way we talk about this is that it is possible for the particle to tunnel through the barrier.
Through the barrier.
Through the barrier, things get weird. So here's one way of thinking about it. In the quantum mechanical world, there are these things called the uncertainty principles. Right? So there's the uncertainty relation. There's one that has to do with energy and time. So the classic one involves The usual one, no, not classical, involves position and momentum. So if I know where something is, I don't know how fast it's going. For example, there's one involving energy and time, which basically says here's one way to interpret it. The amount of energy that a particular part of your system has is uncertain depending on how much time you try to spend measuring it. Right? Now, that involves a whole lot of problems about measuring. In particular, what's the measurement here? But one way, sort of hand-wavy way of thinking about this is, suppose my little alpha particle here inside the nucleus, suppose the amount of energy it has, it sort of comes up to here. Okay? Now, if it could get out here, it would be fine. It would be lovely. Okay? So it's just this barrier it has to worry about. It's got enough energy to sort of exist out here. So within quantum mechanics, the amount of it can borrow that amount of energy for a short amount of time. And so the question is, if I can borrow this amount of energy, there's a certain amount of time, and if in that amount of time the particle actually ends up out here, it will stay out here. Now, this all sounds weird and totally hand-wavy and completely ridiculous, but that's what the model is telling us. In particular, you can do a very sort of simple calculation of how often is this thing trying to get out? How much energy does it need to get over the barrier? So how much time has it got to get here? So what's the probability that it actually gets out? And so when you put all that together, you actually get a pretty decent answer for how often does an alpha decay happen within one of these nuclei. You can actually predict that. Whereas in classical physics, it would say that never happens. Quantum mechanics actually gets the right answer of occasionally it actually will happen.
So I believe it was Gamow who first showed that. I'm trying to remember my nuclear physics.
That sounds about right. It's usually in most things.
Okay, so I'm going to ask you to erase your hill there.
Oh dear.
Right, so the question that we have then is that we have a similar kind of picture here. We have our quarks inside the proton. They're all rattling around. What's the chance that a quark will quantum mechanically tunnel out and escape? So what we need to know is, what does the hill look like? So I'm going to draw the hill. Okay. So the hill looks something like this. So that's inside the proton, and then you have a very steep wall. Oops, like so, and a little turnover. It looks something like that. So this is inside the proton. This is outside the proton. This is basically the strong force holding on to the quarks. So if you ask what energy the quarks have inside, their energy level is down here. Okay, so this is their total amount of energy, and they will thud against this wall many, many times. The problem is that when you spoke about the alpha particle had a certain amount of energy, and if it tunneled to the outside, it would get over the barrier and it would be free. This energy level here is way, way, way below the actual energy the quark would have when it's outside.
Yep.
So there is no lower energy that the quark could tunnel to escape.
Yeah.
Right? So to all intents and purposes, to the quark, this wall itself is infinitely thick.
Yeah.
And if you ask what's the probability that the quark could tunnel out, it's 0. Okay? Effectively 0. So what do? Well, one way you could do this is you could inject energy into here, okay? And this is one of the cool things. You can actually, in the same way as you could put energy into an atom and change the way the electrons are structured around the nucleus, you can put energy into a proton and change the way the quarks are structured amongst themselves. And so you can get excited states of individual particles. But you could put the energy in, but you would need to put in so much energy that you'd get the energy level up to here such that there would be a barrier that you could tunnel through. But the problem is that there's so much energy here, just a teeny bit more, and the thing would fall apart anyway. You'd have overcome the barrier by just injecting more energy.
Yeah.
But then you run into one of the wacky things with quarks and the strong force, is that if you do manage to rip this apart, so if you imagine this gets ripped apart, off these guys go. So imagine this is at CERN, you smash a proton into a proton, the quarks, and so much energy is put in that the quarks get spat out.
Yep.
When you have a lone quark...
Too high.
Too high. Oh no. Come back down here. Let's get rid of this. When you have a lone quark...
Is that one better?
Yes. Here's one I prepared earlier. Like so. When you have a lone quark, the energy due to the strong force actually can provide enough energy to take, if there's a quark-antiquark pair that's appeared in the vacuum, so much energy is associated with the strong force that those quarks can become real quarks. And then, so this can create an antiquark and another quark, which we'll go back and deal with those guys. These guys now stick together due to the strong force, and these form a thing called a meson. So even if you can inject enough energy to separate the quarks, any quark that's left on its own will conjure up other quarks out of the vacuum and join together to create other particles. So we don't see lone quarks in nature. They're always bound together with something.
Right. So the price you pay to make an electron, to make a quark free, is more than enough to buy it some friends.
Absolutely. I think that's a good place to finish.
Yeah, let's end it there.